interested in from propulsion perspective. Once we do that, then we actually got everything we needed from reacting mixture. And hopefully we'll get to the example problem today that will tie up everything we've done from non-reacting mixtures, reacting mixtures, trigonometry, everything. It's a big problem that includes everything, because that's exactly what we're going to do for propulsion systems. And then afterwards we'll start reviewing compressible flows, which is your high-speed air. Okay? So last time, we're going to be doing more example problems on this today, but last time we got a stoichiometric fuel-air ratio, and we said if you wanted excess air or mean fuel condition or excess fuel, all we have to change is our composition mixture here. Now, some of your colleagues had questions over the weekend about, they found examples and whatnot that they had, you don't have to write this down, but they had 3.76 of nitrogen plus oxygen. And if you, got to do it here. 3.76 nitrogen plus oxygen. Well, this takes into account that there's 2 moles of nitrogen and 2 moles of oxygen. In reality here, I'm treating it as, I'm writing nitrogen, but in reality it's an absolute value. So it's the same exact number because it's saying 3.76 multiplied by 2 of nitrogen plus 2 multiplied by oxygen will give you the same value if you take 9.52, which is what we got as A last time. This was our A. If you take this multiplied by this value, that's what you're going to end up getting, and you multiply by this value, that you're going to get 2 primarily, which is this. It'll be 1.9 and a fraction. But it's the same principle. So that was one of the questions over the weekend. Nonetheless, so we're going to be doing stoichiometric conditions and fuel-air examples shortly, but but let me start introducing heat formation and the reference enthalpy. So what if we have a chemically reacting system? So if I have a system of some sort like this, where I have reactants, I have some work, some QNet, and some products. So apply the first law. What do we get? Rate of change of energy over the full line I is equal to W net plus U net plus summation of in and so if this is a reacting system, it's the same exact process that we've done for non-reacting. So we can just say, not that different. From non-reacting. So it's the same principal equations. So all the fundamentals that I need, I already know. The difference comes from the enthalpy. not absolute. Meaning that for each species that I have to deal with, there's a reference enthalpy, and at different temperature levels, that species specifically, now that I have a reacting system, I'm going to be dealing with large gradients of temperature. So therefore, my enthalpy is going to be a function of temperature. And therefore, I could just say, I'm going to use the reference enthalpy and integrate my CPVT. So integrate from some T reference to some T CP dt. And that's the difference between chemically reacting systems of something like this. Still the same first law, still the same conservations. All the differences, I have to bookkeep enthalpy differently, I have to treat it differently. Because I have reactions that are happening. I'm going to get a source of heat from the reaction itself. And we're going to improve that shortly, heat of reaction. Or lower heating value. Some of you dealt with this in the past. So, from that, well, what if I have H in minus H out? So if mass is the same mass I'm putting in, Mi is equal to M out. So I want to be able to take the difference. So H in minus H out. Well, that's going to equal to reference plus the integral of T reference T in CP delta T minus, so this whole thing, minus H reference plus the integral of T reference T out CP T delta T. So from that, I'm making an assumption here that I only have one species to deal with. That I'm putting in some reactants of some sort form and it's coming out the same form. So my H reference here is the same. So this could cancel out with this. And given that this is a minus, I could flip those. And what do I get? I'm going to get H in minus H out is equal to the integral of T out T in CP T delta T. So there's nothing special about it other than the fact that now enthalpy is varying over temperature, a large temperature between the input and output. There's a significant amount of change that's happening there. And I'm accounting for it through my CP delta T. Now, one thing that I'm making as an assumption here, and I just mentioned it earlier, is I'm assuming that I'm magically putting in some species as a reactant that comes out as a product with no change in that species. Now that's not true for chemically reacting mixtures. For chemically reacting mixtures, we're putting in reactants, and we're going to get products. So this is just to demonstrate the equation, but if I want reactants and products, I have to rewrite it into reactants and products. Plus. So if we rewrite it, so if we have reactants and products, what do we get? So H reactants, that's my in, minus H products is going to equal to, now the reference enthalpy for reactants is different than the reference enthalpy for products. So it'll be H reference for reactants minus H reference for products. Plus the integral of T reference to reactants, Cp of the reactants, dt, plus, minus, T reference, unless you flip the integral, T products, Cp of products, T delta T. So that will be our generic form of the equation for reactants and products. Now, what is that enthalpy reference stage? So, reference. So let's say, for example, if I have oxygen, at 25 C and 1 atmosphere. So that's a reference stage that I'm going to use for my enthalpy for oxygen. And I could just say at that stage equal to, at T equals 25 degrees C is equal to 0. And that is my reference point. Nitrogen. And there's a big table in the book. Is equal to 0. Carbon. T 25 degrees C is equal to 0. So the point out of this is I just need to know a reference point that I'm going to determine as my enthalpy and use my integration to the temperature of interest to find out my enthalpy. Question?
Is your reference enthalpy what you consider your enthalpy of formation?
No, not yet. So we're getting there. So that's the heat of formation. We're going to do that. That's getting there, hopefully in the next few minutes. Question?
So in a given problem, if we know a reference temperature and pressure for one thing, one element, then we can just apply it to all of them in the problem?
You're already going to not know the reference for each individual species. So you will know it for all of them. I'm introducing you to the reference state that we always use. Enthalpy is, in this case, it's an absolute value. So it's always relative to a point. So think of it as, what is temperature? Why do we use 0 degrees or 100 degrees for temperature? What is the reference value? Water, right? Water. That's what I use as my reference, but it keeps varying. It's the same principle with enthalpy. So that's what I'm trying to introduce here is the same principle that you dealt with the units of temperature. They use water, 0 degrees C for water turning into ice versus 100 to completely vapor. It's the same principle here. I need some kind of reference to scale my enthalpy accordingly. So in this case, I'm just going to use my reference stage at 25 C, and at atmospheric condition, my enthalpies at a standard species process, it's 0. But as I go to different temperatures, so if I tell you this is at 100 degrees C, well, that's different. So we have to account for that value, which I can do it simply by the integration, account for that over my CP. And it might be negligible enough that I don't have to care about it too much. I mean, if I don't have large temperature gradients, the reason why we have to deal with the integration with Cp delta T is because with combustion and propulsion systems in general, you get larger temperature gradients. So you can no longer say, I'm going to take it as constant. And you will see the effects of that. Okay? Any further questions? Question.
It's Cp as a function of T, not Cp times T, right?
It's Cp as a function of T, correct. This is Cp of reactants as a function of T, delta T. and Cp of products is a function of T, delta T. Where do you see this before? What is delta H equal to? Integral of Cp delta T. Cp, you might have most of the time taken constant, but in this case, Cp is a function of temperature. Okay? Any further questions? All right. So, from there, I could write a generic form for the equation. So let's do the input information. So that's what I'll look at. Let's do input information. So if I have some system and I have some hydrogen and some oxygen and some Q net, I don't know if it's in or out, and what I want as an output H2O in the liquid form. Okay. So I have hydrogen, which is my fuel here, oxygen is my oxidizer that I can burn, and I can get H2O in a liquid form. So what is my chemical equation balance here? H2 plus half, 1, 2, it's going to give me H2O in a liquid phase. So let's apply our first law. The unsteady term is equal to Q net plus work net plus the sum of masses of each individual species minus the sum of the outputs. Now, it's a steady state system, equal to 0, steady state. No work is being done, equals 0, no work. So what do I have? I have the heat is equal to the difference between the mass flow times its enthalpies. So if I say, okay, equal to, or remove Q on the other side, Q net is equal to the output, if I move everything on the other side, so that will be on the positive side. So the m dot H2O multiplied by the enthalpy of H2O liquid minus the input, which I have m dot of H2 H2 minus m dot of O2 H02. Now, assuming that everything is happening here at 25 degrees Celsius and 1 atmosphere, that somehow I'm maintaining that value. Okay, so what happens to my absolute species right here for these enthalpies? What is the enthalpy of oxygen at 25 degrees Celsius and 1 atmosphere? 0. So we're going to refer to this as STP, standard temperature. So this at STP equals 0, this at STP is equal to 0. Now, this is a sort of idealistic situation of this reaction, because what's